Welcome. Today we are going to see the performance of the experiment to determine the overall heat transfer coefficient by heat exchanger. So the requirement for this experiment is, in apparatus we are going to require a suction flask which will act as a steam generator. We will need a condenser, round bottom flask, separating funnel, delivery tube, bend tubes, burners, adapter, beakers, clamps, rubber corks with two holes, safety tube, thermometer, rubber tubes, wire gauze, drum for collecting water, etc. In chemicals we will require water. So now let us see what this experiment, from this performing this experiment, what we are going to conclude. So as you all know, heat, it is a form of energy, and any energy, it has a tendency to move from a region of higher temperature to a region of lower temperature. So heat transfer, we can say it is a dynamic process and it occurs on its own. That is, we can say it occurs spontaneously. So to bring about heat transfer processes, the equipments which are used are called as heat exchangers. So heat exchangers, they are used for heat transfer between any two fluids. Okay, now fluids, they consist of gases as well as liquids, right? So heat exchangers, they can be used to bring about heat transfer in between gases, or heat transfer in between liquids, or heat transfer between gas and a liquid. Okay, so for both the forms we are going to use heat exchanger. So it can be used for both heating and cooling purpose. Okay, heat exchangers are, they are not only used for heating purpose, but they can be also used for cooling purpose. So these are widely used in space heating, refrigeration, air conditioning, and pharmaceutical and food industry, etc. So on the basis of direction of the flow of both the fluids, these are classified as parallel flow or counter current flow and cross current flow heat exchanger. Okay, now if you see this diagram, this shows parallel flow. Okay, now what do you mean by parallel flow? Look, now this is the hot fluid. Okay, suppose we want to cool this hot fluid, right? So this, what we are going to do by using a heat exchanger, we will cool this fluid, right? So for that, what we need to do, we will pass this hot liquid through the inner tube and the cold fluid will pass through the outer tube, right? Now what will happen due to this, there will occur heat transfer. Okay, as you all know, heat is a form of energy. It moves from higher temperature to lower temperature, right? So this hot liquid, it will give, or the hot fluid, it will give its heat to the cold fluid, right? So what will happen, as the hot fluid will flow along its length, it will get cooled, right? Now if you look at it carefully, look at the diagram carefully, this the direction, this is the direction of the flow of hot fluid, right? It is moving towards your right. Now the cold fluid is entering at this point and it is also moving in towards the right side, right? So now if you see this, the arrangement, it is parallel. Okay, the direction of flow of both the fluids is same. Okay, so in this case, this type of flow is said to be parallel flow. Okay, now next we will see this diagram. Okay, here you have counter current flow. Now what is the difference? Here the fluid which you want to cool, it is flowing towards the right, but the fluid which you are using to cool down this fluid, it is flowing towards the left, right? It is flowing towards the left. So the direction of flow is opposite and hence it is said to be counter current flow, right? Now if you observe this figure, this is the cross current fluid. From here you are going to uh, make inflow the hot fluid at this point and the cold fluid will move from this point. Okay, so this type of arrangement is said to be cross current. Okay, they are crossing one another. Okay, so on the basis of the flow pattern of both the fluids, the heat exchangers, they are of three types: parallel flow, counter current flow, and cross current flow, right? So now let us see the relationship between overall heat transfer coefficient and inlet and outlet fluid temperature. The heat exchangers, they are analyzed using either two methods. Okay, we have two methods for analyzing the heat exchangers. Okay, we want to um, see in what type of heat exchangers will act as a highly efficient system. Okay, so for that, for analyzing the heat exchangers, we can use two methods. One is logarithmic mean temperature difference, which is commonly called as LMTD method, or effectiveness number of transfer units. Okay, it is epsilon NTU method. Okay, these two methods are used. So LMTD is the most commonly used method. It is a method which is used to determine the overall heat transfer coefficient. Okay, more is the heat transfer coefficient, more efficient is your system. Okay, so in LMTD method, overall heat transfer coefficient determination is based on the measurement of the inlet and the outlet fluid temperatures. Okay, means if for this parallel flow we are going to use LMTD method, then we will require this temperature, we will require this temperature, we will require this temperature and this temperature, right? So whereas in case of epsilon NTU method, it is used for prediction of the outlet temperature. Okay, we are not going to here measure the outlet temperature, we are going to predict it. Okay, so if, it based on the prediction of the outlet temperature if the heat transfer coefficient and inlet temperature are known. Okay, so based on this we will determine the efficiency. So in a heat exchanger, whenever heat transfer takes place, the rate is determined. Okay, now the rate of heat transfer, it is given by the equation Q is equal to U into A into delta Tm. Okay, now we will see what are these values. Q stands for rate of heat transfer, U is the overall heat transfer coefficient, A is the surface area across which heat transfer will take place, delta Tm is the mean temperature drop. Okay, so delta Tm is used instead of delta T. Okay, we are going to calculate a mean temperature drop, and we are not just going to take delta T, not just temperature drop, because why? Because the temperature drop, it varies with the position of the hot and cold fluid inside the heat exchanger. Okay, now we will consider a double pipe heat exchanger. Okay, suppose the cold fluid is flowing from the outer pipe and the hot fluid is flowing through the inner pipe, like we have seen in the previous examples. Okay, then the temperature of both hot and cold fluid, it will vary depending on their position. Okay, so at point A, the cold fluid will have higher temperature as it is close to the wall of the pipe through which hot fluid is flowing. At point B, the fluid will have low temperature as compared to point A. Similarly, at point C, the fluid will have higher temperature as compared to point D as its wall is enclosed by cold fluid. Hence, we are going to consider a mean temperature drop. Okay, now here we have this diagram. Okay, so now the temperature you can see here. Okay, the temperature of the hot fluid, it varies depending on its position, right? So at point A, this point is very close to the inlet, and this point B, it has to be here. Okay, that means it is showing the temperature over here, right? So the temperature at this point will be high as compared to the temperature at this point. Now why? Because the hot fluid is entering from this point, and on its way, okay, all over this length, slowly it is getting cooled off because of heat transfer, right? So automatically at this point the temperature of hot fluid will be reduced. Okay, so there will be a difference. So we can say the temperature of point A is greater than the temperature at point B, right? Now, if you see these two examples, the temperature at point C, it will be higher as compared to the temperature at point D. Now, why? Because here the cold fluid, okay, is far from the C point, whereas the cold fluid, it is immediately close to this point, right? So, heat transfer at this place will be greater as compared to the heat transfer at this place, right? So, we can say the temperature at point C will be greater as compared to the point D. Okay, so temperature drop, it also sorry. So now if you see this example, okay, now is the temperature drop constant over all this length? So the answer is no. Here the temperature is more, here the temperature is less. Okay, here the temperature is more, here the temperature is less. So as the temperature drop is not constant, we cannot directly use delta T. Okay, if we use this value for these 2 points, then the answer will be different. Okay, and if we use delta T for these 2 points, then the answer will be different. And hence we don't use delta T, but we calculate the mean for this uh, system, and we use delta Tm, right? So the temperature drop, it also varies significantly with the type of the exchanger. Okay, so consider that heat exchangers. Okay, I'll show you the diagram. So here you have to consider that you have two types of flows in the heat exchanger. Okay, so in all the flow, Thi will be the temperature of the hot fluid at inlet, and Tho will be the temperature of the hot fluid at the outlet. Tci is the temperature of the cold fluid at inlet, and Tco will be the temperature of the cold fluid at the outlet. Okay. Now consider the following flow of the fluids. If the flow is parallel, then the fluid flow will be represented like this. Okay. Now you have to consider that you have two tubes. This is the inner tube and this is the outer tube, right? The hot fluid is flowing in this direction parallel, the cold fluid is flowing in this direction, cold fluid is moving in this direction, right? So now this is the parallel flow. Okay, so this is the length. Okay, this is this part on the T side and this is the part on the C side. Okay, sorry, this will be H. Okay, so we can say this is the H side and this is the cold side. Why? Because here you are flowing in the hot fluid and here it is the outlet for the cold fluid, we can say. So now what will happen? Consider, suppose your fluid is flowing from this point to this point. On its way it is giving out its heat to the cold fluid, right? Cold fluid is also flowing in this direction. So we can say this inlet of hot fluid is at this temperature. The inlet of the cold fluid here, it is at this temperature. Okay, so the difference in between this temperature is the delta Thi, difference in the temperature of cold fluid and difference in the temperature of hot fluid. Okay, at this end, that is represented as delta delta Ti. Okay, now as it is flowing through this length, so what happens? The hot fluid, it is giving off its energy to the cold fluid, so the temperature of the hot fluid is decreasing, and as this cold fluid is moving through this point, it is taking up the heat from this hot fluid, right? So the temperature of the cold fluid will increase slightly, right? So now at this end, the temperature of the cold fluid will be represented as Tco, and at this point, the temperature of the hot fluid will be represented as Tho, right? Now, if you see this, this will be the temperature difference between the hot and the cold fluid along the path. Okay. Now consider it to be a counter current flow. Now you have to consider the same example, only what is different? The cold fluid is moving in this direction and the hot fluid is moving in this direction, right? So now what will happen? Now this Thi is the temperature of the hot fluid, and this Tci, it has to be here. This is the temperature of the Tco, this is the temperature of the cold fluid outlet at the outlet. This is the temperature of the hot fluid at the outlet, and this is the temperature of the cold fluid at the inlet. Why it is why this is like this? Because the flow is in opposite direction. Okay, so as the fluid it is moving, the hot fluid, if you see here, this is the cold, this is the hot, and this is the cold. So here at this point, this fluid is extremely cold, and at this point the hot fluid is extremely hot. Okay, so now what will happen? As this fluid is moving in this direction and this is moving in this direction, there occurs heat transfer. Okay, so uh, the temperature of the hot fluid, it decreases more. Okay, why? Because the cold fluid at this point, it is at very low temperature, right? And this cold fluid at this point is very cold. So when it moves, its temperature will increase at the outlet. Okay. Now if you see this, now why this difference in both the temperature is small? Because as the hot fluid is moving over this length, okay, when it comes at this point, already it has lost its heat to the cold fluid which is flowing externally, and when it reaches at this point, its temperature is decreased. Okay. Now the cold fluid is moving in here, so its temperature is also low, so the difference in the temperature here at this point is small. Okay. Now as the cold fluid is moving along this path, it is getting heated up. So the temperature of the cold fluid is increased at this point, and here you are putting in the hot fluid. Okay. So at this point, the drop in the temperature, it will be small. Okay. Now if you see this, the temperature drop is highest at this point and it is lowest at this point, but the case is different here. Here also the temperature difference is small, and here also the temperature difference is small. Okay. So it is given as delta T. Now if you compare this to delta T's, then obviously we can say that this delta T, it remains more constant overall this length as compared to this delta T. See, you can see the difference here is so large, and then it reduces to this point. But here the distance is this, the temperature difference is this much, and it is not increasing to that level, right? So here we can say, as the temperature difference is small, we will get or the temperature difference is constant all over this length, we will get good heat transfer coefficient in this case. So from the above diagram, it is very clear that a parallel flow heat exchanger will require maximum surface area for heat transfer as compared to that required by the countercurrent flow heat exchanger. So rate of heat transfer is more efficient in case of countercurrent flow exchanger. So the mean temperature drop is calculated by LMTD method as delta Tm. Okay, first we are going to calculate the delta Tm. Delta Tm is equal to delta Ti minus delta To upon inverse log of delta Ti by delta To. Okay, so this is the equation for delta Tm. Okay, so as we know, this is the case. Okay, inverse log of x is equal to 2.303 into log x. So the same equation we will write as delta Tm is equal to delta Ti minus delta To upon log of delta Ti by delta To into log of delta To by delta T. Okay. So for parallel flow, we can say delta Ti. Now what is the temperature at the inlet? Delta Thi minus delta Tci. The temperature of hot fluid at inlet minus temperature of cold fluid at inlet. And delta To is the temperature difference between hot fluid and cold fluid at the outlet. Okay. So we can write equation 3 as delta Tm is equal to delta Thi minus delta Tci minus delta Tho minus delta Tm is equal to Thi minus Tci minus delta Tho minus Tco divided by 2.303 into log of Tho minus Tco upon Thi minus Tci. Okay. So this is the equation for mean temperature difference for parallel. Okay. Now we will see for countercurrent. Delta Ti, temperature difference at inlet is Thi minus Tco, and delta To is equal to Tho minus Tci. So equation 3 for countercurrent can be written as delta Tm is equal to Thi minus Tco minus Tho minus Tci upon 2.303 into log Tho minus Tci upon Thi minus Tco. So in order to determine the overall heat transfer coefficient, equation 1, if we rearrange the equation 1, we get overall heat transfer coefficient is equal to Q upon A into delta Tm. So here Q is the average rate of heat transfer. So Q is the average of heat lost by the steam and heat gained by the circulating water. So now when the steam, it will lose its heat, some amount of heat is transferred as latent heat accompanying phase changes. So here the steam goes from gaseous state to the liquid state. So when the circulating water it is heated, there is just increase in its temperature and is not accompanied by phase change. Okay, this is very important. When steam is going to lose its heat, some amount of heat it is transferred as latent heat, which will accompany the phase change. Why? Because gaseous state is getting converted into the liquid state. But when you are only using water or only using any type of liquid, then there occurs no phase change. Okay, so this when you are using any liquid, so it is free of latent heat changes. Okay, so in this case Q is equal to Q1 plus Q2 by 2. So now what is Q1? Q1 is the heat lost by steam along with latent heat of condensation. Okay, so here we will have to consider the latent heat of condensation. So Q1 can be written as Q1 is equal to M1 S1 T1 plus M1 L. M1 is mass of the steam or the condensate. S1 is the specific heat of water. T1 is temperature drop between steam and condensate. L is the latent heat of condensation of steam. So the specific heat is the amount of heat. Now here you can see the specific heat. Now what is specific heat? It is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. So this specific heat of water is 1 calorie per gram degree Celsius. So it can also be written as 4.186 joule per gram degree Celsius. Now note that the enthalpy of condensation or heat of condensation is by definition equal to the enthalpy of vaporization. Just the sign is opposite. Okay. So Q2. Now what is Q2? Q2 is the amount of heat gained by the circulating water. So Q2 is equal to M2S2T2. Now M2 is equal to mass of water which is circulated. S2 is the specific heat of water and T2 is the temperature rise. Okay. So the principle of this experiment is when two fluids they flow through a heat exchanger, there occurs heat transfer from a hot fluid to a cold one. The heat transfer between two fluids separated by a solid thin film take place by convection and conduction. So in this case, the temperature of hot fluid it is going to fall and temperature of the cold fluid it will increase. So the rate of heat transfer through fluids is determined by using overall heat transfer coefficient of liquids. So here the rate of heat transfer, it is a product of overall heat transfer coefficient, surface area of this heat exchanger and the temperature drop. So rate of heat transfer Q is equal to U into A into delta T. So U is overall heat transfer coefficient. So A is the surface area across which heat transfer will take place and delta Tm is the temperature drop. Okay, so now in this experiment we will calculate the delta Tm, okay, by LMTD method. Okay, so overall heat transfer coefficient it can be calculated as U is equal to Q divided by A into delta Tm. Okay, so this is our final equation, and because using this equation we will calculate the overall heat transfer coefficient. Right, now we'll see how the experiment is performed.
Now we are going to see how we are going to perform the experiment. Okay, now if you see this setup, here this is the steam generator. Okay, we have corked this steam generator with a rubber cork having two holes. Okay, from one hole we have inserted the the safety tube, and through the second we have inserted the thermometer, right? So this thermometer is going to give you the temperature of the steam, which is your hot fluid, right? Now the steam generator, with the help of this rubber tubing, it is connected to a bent tube, and that bent tube is connected to the condenser. Okay, now from our steam which is generated there, it will move from the inner tube, and the fluid, okay, the cold fluid which we are going to use for cooling, that will be circulated from the from the outer tube, right? Now this condenser, we are going to perform today two processes. One is parallel flow and the second is counter current flow. Okay, so parallel flow will be when we will connect this tube to the inlet of the cold water, and the outlet will flow away. Okay, that is parallel flow. And in the next process, which is counter current flow, we are going to connect this inlet with the tube with the tap, and this from this outlet the cold water will be released. Okay, now keep in mind we have to measure the volume as well as the temperature of the water which is flowing from the outlet of this condenser. Okay, so that water is important and we will collect it using a drum. Okay, so after your steam it passes through this condenser, it will get cooled because of the heat transfer process between the hot fluid and the cold fluid, right? So as it will move along this path, along this length, it will the steam it will get condensed and it will form liquid water, and that liquid water it will be collected in this receiver with the help of this adapter. Okay, the condenser is connected to the adapter and that adapter is connected to the receiver. Okay, so all the water will be collected. Now the procedure for this experiment is, first we have installed all the setup. So what are we going to do now? First we will start the burner. Okay, the steam will be generated. We are going to measure the temperature of the steam, right? Now once the steam it will come in this condenser, and at the point when it will start to condense, okay, after that when we receive one drop of the condensate, then what we are going to start collecting the water. Okay, this is for counter current. Okay, then we will start collecting the water, right? We will carry out this process for 5 minutes, right? Now once that 5 minutes are over, what we are going to do, we will measure the temperature of the water, okay, which is collected in the drum, and also we will measure its volume, right? Also we are going to measure the temperature of our distillate. Also we are going to measure its volume, right? So that will be required for our calculation. The second thing what we are going to do now, after that, is we will arrange the setup for parallel flow. Okay, then the water flow will be from here to the condenser and outlet will be here. Again what we are going to do, we will start the steam generator. We will measure the temperature of the steam. When our steam will get condensed here, after that, when we get first drop of the distillate, we will run this assembly for 5 minutes, and after that we will measure the volume and the temperature of this distillate, and we are going to measure the volume and the volume and the temperature of the water which we have used for cooling process. Okay, that water also we are going to collect and we will measure its volume and temperature. Okay, so this is the general setup and the process. Now we will proceed with the procedure. Now we have started the burner and we will wait till we get the steam. Now as steam has started to come out, we are going to check the temperature of the steam. So the temperature of the water, if you look at this thermometer, it is up to 100 degrees Celsius. So we can say the temperature of steam is now at 100 degrees. Okay. So now from here the steam has started to come into this condenser. Okay, the steam it has started to condense on its way. Okay, so now the steam has also started to condense. As we are going to get the first drop, we will wait till we get the first drop of clear water or clear condensate. After we will get the first drop of the condensate, we will collect the water. Okay, the water which is getting removed from the condenser. Okay, so now the condensate has started to come. Okay, so now we are going to capture the water. So now we are going to collect the water in this drum and we will run this assembly for 5 minutes. Okay. So now the time starts now for further 5 minutes. So now if you see, the distillate is being collected. See, the steam is now coming into the bent tube. From there it is moving into the condenser. So if you look at the bubbles, those bubbles, these are due to the heat transfer that is occurring there.
latent heat रिमूव के लिए
If you see this at this place, you are getting a continuous flow of the distillate. Okay, so the distillate is running continuously. Okay, and in 2 minutes we have collected this much distillate. Now we are at the end of our 5 minutes. So now as our time is up, okay, now we will dismantle this assembly, and if you look at this distillate, we have collected a well amount of distillate just within 5 minutes. Okay, now we will remove this setup and we will measure the temperature of both the distillate and the water which is removed of the water collected, and we will measure the volume of the water collected, as well as we will measure the volume of the distillate, and we will measure the temperature of both the water collected and the distillate. So now we are going to dismantle this, or we will remove the receiver, and we will check its volume. So if you can see here, the volume is now approximately 9.9 ml. So we have received 9.9 ml within 5 minutes. So this 9.9 ml of the distillate I have taken out in this beaker, and now we will take its temperature. So the temperature of this distillate is approximately equal to 34 degrees Celsius. The temperature of the distillate is 34 degrees. Now this is the water which we have collected from the condenser, and first we will measure its volume and then we will measure its temperature.
fine.
The volume of the collected water is nearly equal to 495 ml. Now this is the remaining water. First it was 490 ml, and this is the remaining water. Plus 500. Total volume of water is 990 ml, and we will measure its temperature now. The temperature of this collected water is 40 degrees Celsius. Now we will see the next part of the procedure, and that is we have to make this equipment to operate for parallel exchanger. Okay, now if you can see here, this point has become the inlet and this point has become the outlet. Okay, so now we will wait till we get the steam, and once we collect the first drop of the distillate, we will wait for 5 minutes and then we will measure the volume and the temperature of the distillate. So we will wait till we get the steam. So now we have received the first drop of distillate, and we will collect the water and we will run this operation for 5 minutes. So now we are collecting the water and we will wait for 5 minutes. Okay, so the assembly is going to operate for the next 5 minutes. Now if you take a look, we are getting a continuous stream of the condensate. Okay, so we have completed our 2 minutes. Now still 3 minutes are to go. So we will run this assembly for the next 3 minutes. We are collecting the water, we are collecting the distillate. So we will wait for 3 minutes. So now we are at the end of the 5 minutes, and now we will dismantle this assembly and we will measure the volume and the temperature. So we have now switched off the burner. We will switch off, we will close this tap. Okay, now we will remove this receiver and we will measure the volume and the temperature. Okay, so now this much amount of water we have, or the distillate we have received. So this is it, we have received 9 ml of the distillate. It is 8.9 ml of the distillate is received. Okay, now we will measure the temperature of this. Now we are going to measure the temperature of this distillate. And the temperature of this distillate is 24 degrees. The temperature is 24 degrees, right? So now we will measure the volume of this collected water. So this is the first 500 ml of the water. This is the next 500 ml. That means we have measured 1000 ml. This is 1500. This is 1500
temperature.
And this is the last 500 ml. Okay, so we have collected 2 liters of the water and we are going to measure its temperature. The temperature of this water is 22 degrees Celsius. Okay. So now we will proceed further with the calculations for this experiment.
Now let us see the observation table. So the length of the condenser was 42 centimeters and the radius of that condenser was 0.8 centimeter. So the area of condenser was calculated using the formula 2 pi RL plus 2 pi R square. So the area of our condenser was 214.85 centimeter square. Now let us see the calculations for amount of heat gained and loss for countercurrent flow. Okay. So now first we will see the observation table for heat lost by the steam along with the latent heat of condensation. So here we have the volume of condensate and it was found to be 9.9. The specific heat of water is 1. Temperature of the steam was found to be 100. Temperature of condensate was found to be 34. Temperature drop between steam and condensate is 100 minus 34 is equal to 66. The latent heat of condensation of steam is 540. So now we will see the calculation for calculating the amount of heat lost by the steam, and that is denoted as Q1. So Q1 is equal to M1 into S1 into T1 plus M1 into L. So by substituting these values, we get the amount of heat lost by the steam as 5999.4. Okay, now let us see the observation table for the amount of heat gained by the circulating water, which is Q2. So it is the water temperature at inlet was 20, water temperature at outlet was found to be 40 degrees Celsius. So temperature rise we will say is 40 minus 20 is equal to 20 degrees and the specific heat of water is 1. So volume of water at the outlet was found to be 990. Now let us see the calculation for calculating the amount of heat gained by the water, which is denoted as Q2. So Q2 is equal to M2 into S2 into T2. By substituting the values and performing the calculation, we get the amount of heat gained as equal to 19800. Okay. So the average rate of heat transfer, which is Q, is the average of Q1 plus Q2. Okay. So by substituting the values, we get average rate of heat transfer as 12899.7 calories. So for parallel flow, we will perform the same calculations. So this is the observation table for heat lost by the steam along with the latent heat of condensation. So the volume of condensate was found to be 8.9. Specific heat of water is 1. Temperature of steam was 100. Temperature of condensate was 24. So temperature drop was 76. The latent heat of condensation of steam is 540. Now let us see the calculations for amount of heat lost by steam is Q1 is equal to M1 into S1 into T1 plus M1 into L. By substituting the values, we get the final value of amount of heat lost to be 5482.4. Now this is the observation table for the amount of heat gained by the circulating water. So inlet temperature of water was 20. Outlet temperature here it was found to be 22. So temperature rise of the circulating water was by 2 degrees. The specific heat of water is 1 and volume of water at the outlet was found to be 2000 ml. So let us see the calculations for amount of heat gained by the water. Q2 is equal to M2 S2 T2. By substituting these values, we get the value to be 4000. So the average rate of heat transfer Q was found to be 4741.2. Right. Now for parallel flow, we have to calculate the mean temperature drop. So the formula for it is delta Tm is equal to T1 minus T3 minus T2 minus T4 by 2.303 into log of T2 minus T4 upon T1 minus T3. Okay. So here we will substitute the values here and we get the value for delta Tm for parallel as 32.91. Okay. So the overall heat transfer coefficient for parallel flow U is equal to Q divided by A into delta Tm. So now we have all the values for the quantities at the right side, right? So we will substitute those values. So Q was found to be 4741.2 into area was 214.85 and mean temperature drop was 32.91. Okay, so by carrying out these calculations, we get the overall heat transfer for parallel flow to be 0.67. For counter current flow, the formula for delta Tm is T1 minus T4 minus T2 minus T3 upon 2.303 into log of T2 minus T3 by T1 minus T4. So by substituting these values, we get the delta Tm as to be 44.90. Okay, so though here you are going to get a minus sign, but in heat transfer process, heat transfer is taking place, so there is loss of heat. Okay, so we are not going to consider that minus sign in the calculations for heat transfer. Okay, so we will just take the log of 6 by 80. Okay, so we get the final answer to be 44.90. Now we will determine the overall heat transfer coefficient for parallel flow as U is equal to Q divided by A into delta Tm. So we have all the values for the quantities on the right side. So we will substitute those. Q is 12899.7 into area is 214.85 into delta Tm is 44.90. So the overall heat transfer coefficient for a counter current flow was found to be 1.337. So now we will write the result as the overall heat transfer coefficient for parallel flow was found to be 0.6705, and the overall heat transfer coefficient for counter current flow was found to be 1.337, right? So by just looking at these values, you all can say that the heat transfer coefficient for the counter current is highest. That means heat transfer here will be more efficient as compared to parallel flow. So we can conclude that as the overall heat transfer coefficient for counter current flow is higher as compared to that of parallel flow, it can be concluded that heat transfer is more efficient in the counter current flow than in parallel flow. Okay. So now let us see what are the most frequently asked question here. The first question is either you'll be asked to write the applications of heat transfer process. So you can very easily say that heat transfer process is used in the process of drying. It is also used in the process of heating, or it is also used in the process of evaporation. Okay, so these are the different operations. Or boiling also there occurs heat transfers for solubility. For some substances we increase the solubility by heating the substance. Okay, so these are the applications of the heat transfer process. Okay, sometimes you will be asked to write the mechanisms of heat transfer process. So you all should know that there are basic three mechanisms of heat transfer. First is by conduction. Now conduction, it takes place only in case of solids, and there occurs no actual movement of the solid molecules, but heat is transferred in the form of vibrational energy from one molecule to another, and in this way there occurs heat transfer in case of conduction. The second mechanism is convection. Convection takes place in fluids. Now fluid can be a liquid or it can be a gas. Okay, so during convection there occurs actual movement of the molecule from one place to another, and this results into heat transfer process, right? And the third is the radiation. So what happens in the radiation? Here um, heat is transferred in the form of electromagnetic waves. Okay, so whenever an electromagnetic wave it falls on any object, amount of heat is reflected, it is transmitted, and amount is absorbed. So it is that amount of radiation which is absorbed, it is converted into heat. The third question will be define Fourier's law. Now this is very favorite and important question. Here you have to say that Fourier's law tells us that the rate of heat transfer is directly proportional to the area. It is directly proportional to the heat transfer or the temperature drop, and it is inversely proportional to the path length through which the heat has to travel. Okay. Now the next question is very typical, and it is what type of flow shows better heat transfer and why. So we have just performed the whole set of experiment to prove that the overall heat transfer coefficient of counter current is the best, and hence that type of flow will show you the good rate of heat transfer. Okay, And the last question will be, give any two examples of heat transfer exchangers or heat exchangers. So the best example is tube and shell heat exchanger. Then second is multi-transfer, multiple pass heat exchanger, and floating head heater. Okay, so these are the different examples of heat exchanger. So we have completed the experiment of determination of heat transfer coefficient. Thank you for watching.